Hello, my name is Katherine Hendrickson. I'm a PhD student in Dr. Matthew Hale's core lab at the University of Florida. I'm excited to be sharing our work towards totally asynchronous primal-dual convex optimization in blocks with you virtually today. So jumping right in, we're interested in solving constrained convex optimization problems that have the form shown here, minimizing some function h of x that is subject to some constraints g of x. Not only do we hope to solve this type of problem, we want to do it in a distributed, asynchronous way. Problems of this form are used in many applications, including large-scale machine learning problems, robotics, networks, and communications. Our goal is to present a new way to solve these problems that allows for parallelization across agents, whether those are processors, drones, systems, controllers, etc. In addition to parallelization, we present an algorithm that is as tolerant to asynchrony as possible, and I'll get into that more in a minute. But first, a little background about where our work fits in. In this slide, we have broken down common approaches into four main areas: unconstrained versus constrained optimization, and overlapping methods, think averaging, versus block-based methods, where every agent is responsible for their updates and communications. Unconstrained and overlapping methods have agent I update their copy of the primal variable, and then all agents average over the graph. In overlapping and constrained methods, agent I is updating a primal-dual pair instead, and these pairs are then averaged. In block-based, unconstrained approaches, agent I now updates only the ith block of x. These blocks are then shared, rather than averaged, among agents. Finally, our focus: a constrained, block-based approach. Here, a primal agent I updates only the ith block, xii, dual agent C updates only the block mucc, and then agents share their updated block values. Our approach has four basic steps. First, we form a Lagrangian using KKT multipliers. We then have a primal-dual optimization problem of which we are interested in finding the saddle point. In order to guarantee strong concavity, we then regularize. Because the Lagrangian is defined in mu, we use a Tikhonov regularization in mu to form a regularized Lagrangian. A lesson from literature is that curvature matters. To prevent the Lagrangian from flattening, both strong convexity in x is needed, along with strong concavity in mu. Regularizing provides this strong concavity in mu. As for strong convexity, we'll explore this later by considering a certain class of problems. Next, we begin strict parallelization by assigning updates. The primal variable x is distributed in blocks among a number of primal agents. Each primal agent I stores a copy of the primal variable locally, denoted xi, but is responsible for updating only the ith block, xii. Similarly, the dual variable mu is distributed in blocks, with dual agent C storing mu C locally and updating mu CC only. Finally, the agents perform a gradient update. We chose a gradient update law because first-order methods have some degree of inherent robustness and involve simple computations. Primal and dual agents individually perform the gradient updates you see on the slide. This algorithm is the focus of both the entire paper and this talk. Each primal and dual agent perform updates for their blocks using their locally stored primal and dual variables. If applicable, this update is then projected onto a constraint set. Our analysis relies on three tiers of assumptions. Given this form of a problem, we first assume that we are minimizing over a convex function h of x. We then assume that the function exhibits behaviors that aid in analysis and convergence. First, that h is twice continuously differentiable and convex, that g satisfies Slater's condition and is twice continuously differentiable and convex, and that the set x is non-empty, compact, and convex, and can be decomposed. For example, these assumptions let us minimize convex polynomials over box constraints, as well as a wide range of other problems. And these assumptions are satisfied by several common problem formulations from the areas I mentioned earlier, including in machine learning and autonomy. Finally, we impose an assumption of diagonal dominance on the Hessian matrix. The surface plot on the bottom right gives a visual of what this entails. The absolute value of every diagonal value of the Hessian matrix is at least beta greater than the absolute values of the entries on the rest of the row. If the original Hessian matrix is not diagonally dominant, then regularizing with respect to X will provide diagonal dominance. However, we don't necessarily need to regularize here because a problem that already satisfies this assumption doesn't need it, and we can solve such problems without incurring a regularization error. In addition, while this assumption is perhaps less common than the others we've made, its use dates back several decades, and it has appeared over time in the optimization and scientific computing literature. So in short, some problems give us this for free, and others may need to be regularized, though both paths get us to this point. Now finally, looking at asynchrony. There are two major ways a primal or dual agent may be asynchronous: in updates and communications. First, looking at primal agents, those that are responsible for updating and communicating the primal variable blocks. We allow primal agents to communicate completely asynchronously. At any time step, primal agents may or may not update and do not have to synchronize their updates in any way. Here, primal agent 1 does not update at this first point in time, indicated by the dashed arrow, while primal agent 2 does update, indicated by the solid arrow. Over time, each one can update at any point in time, independently of all other agents. We also allow primal communication to be entirely asynchronous. Primal agents communicate their updates whenever they wish to any combination of primal and dual agents. Similarly, we allow dual agents to update completely asynchronously. However, we have to be careful with complete asynchrony in communication. While dual agent 1 may communicate at a different time than dual agent 2, the primal agents must agree on the dual variable they're using in updates. I won't go into the details of the counterexample, but in the paper, we show that this could actually stop us from converging at all. This is because each new dual update corresponds to a new problem for the primal variable to minimize over. If different primal agents have different copies of mu, they're essentially all working towards minimizing different problems. We handle this practically in two ways. First, for simplicity of analysis, we stipulate that a dual agent communicates an update to all primal agents at once. Second, for practical implementation, we require that dual agents include an iteration count with their communication. This allows primal agents to compare their versions of mu. We do allow arbitrarily long delays as long as no agent stops updating or communicating entirely. So with all of that introduction behind us, we can look at a very high altitude view of our algorithm. First, primal agents asynchronously perform gradient descent to update their primal block. Although these steps may appear in sequence in the diagrams, they happen asynchronously. Not necessarily in the sequence, not necessarily at the same frequency, and not necessarily with any regularity in their timing at all. Next, primal agents asynchronously communicate their updates to other primal and dual agents. Once a dual agent has received updates from all primal agents, they update their block with gradient ascent. Dual agents may perform these updates at different times. Finally, after a dual agent has completed an update, it communicates this update, along with an iteration count, to all primal agents. And now, looking at primal convergence from Theorem 2 in our paper. For a fixed dual variable, we are considering the distance of the primal variable onboard primal agent I, xi, from the optimal value, x star. We are measuring this distance with the max vector norm. This distance has an upper bound that is pre-multiplied by a term between 0 and 1, which is raised to a term, ops kt. This ops term counts primal operations, which is determined by the number of primal updates and communications across all primal agents. The operation counter increases by 1 once all primal agents have computed at least one update with a given value of mu, and then they communicate these updates to all other agents that need it. Our proof relies on these nested invariant sets shown here. Essentially, this is like a Lyapunov stability proof, and we show that operations move primal agents forward, and also that they are never driven backwards, even under asynchrony. So you either make progress towards a solution or wait, but progress is never undone. And now the more complicated upper bound, looking at dual convergence. You'll immediately notice that there are additional terms on the right-hand side that may preclude convergence. We presented an earlier version of this theorem in our CBC paper that included a term that we called the asynchrony penalty. This term stops us from having zero distance to a dual optimum, and the analysis reflects that this is due to asynchrony, which is why we have called it the asynchrony penalty. Theorem 3, as presented in this slide, is a preview of our current work reducing this asynchrony penalty, while also looking at blocks larger than scalars. We have transformed that original term to one that is pre-multiplied by the dual step size row. This implies that there's a possibly significant trade-off between performance and error. We're working towards further defining this error and its implications. Certain types of problems, such as ones where constraints are separable, may lead to further reduction or removal altogether of this term. The final term in the theorem is again pre-multiplied by the primal convergence rate raised to some ops term, of which there is much more discussion in our paper. The term is minimized when primal agents are allowed to make progress with the previous dual variable prior to another dual update. We also include a simple numerical example in our paper of the form on the slide. When the objective function was modified to increase the diagonal dominance, we found that stronger diagonal dominance correlated to faster convergence. However, sufficiently weak diagonal dominance provided similar results. We believe this is because a small beta leads to equally weighing both minimizing H and satisfying G. The interplay between different parameter choices is the focus of future work. In conclusion, some of the work we're currently doing is a direct expansion of that presented in our CDC paper. We're further clarifying the asynchrony penalty and the implications concerning problem formulation and practical application. We're also examining the effect of dual update frequency. We believe that too frequent updates may lead to slower convergence. We are also implementing the algorithm with more complicated objective functions and parameters, such as the interplay between diagonal dominance and communication rates in the figure on the right. Finally, we are publishing the algorithm in Python and GitHub. Please contact us if you have any questions or thoughts on our work. We're really excited about the work that we're pursuing, and we're so thankful for the opportunity to present some of it with you virtually here today.